Welcome, everyone. Lecture 5 already, right? I mean, time flies when you're having fun. So we're roughly at 1/3 of the entire course, of the entire semester already. And that's, yeah, there's that. We're going to be continuing on classification. Last week, I showed you that, well, rather than having a continuous target variable that we want to predict, we can use a lot of the same machinery that we've learned how to predict a categorical attribute, right? Essentially, well, even just linear regression works, in very select cases. But if we apply essentially a fancy activation function, the logit, all of a sudden, logistic regression does an amazing job. I told you earlier in the course that k-nearest neighbor is one of those methods that everybody loves and hates, right? If you treat it right, it does an amazing job, right? It's difficult to beat. Of course, if you have a very difficult problem, high dimensional, okay, then you need to be very careful. It's difficult to beat. Logistic regression is also one of those methods. It's also one of those methods that if you treat it not entirely stupidly, it is very difficult to beat. And in fact, I already hinted at it last week, in fact, many way more advanced methods for machine learning, and including actually a large class of deep neural networks, are essentially very fancy instantiations of logistic regression. Right? What is the main difference? The main difference is that in plain logistic regression, we give our linear regressor some features, and then, well, there's some linear combination of those we find out. Deep learning, essentially the only between quotes magic it does some pre-processing over these features, such that we, in the end, in the pre-final layer of the network, we don't have the raw input features, but we have some pre-processed features. And on those, we do logistic regression in entire classes of deep learning, and so on and so forth. So logistic regression is really just there. I also promised you last week to let you to sample, and I hope that the video setup works right now, in the audio particularly, to let you hear the sound of machine learning. So let's get started with that before we continue with some new methods that somehow give a twist. We're going to be doing something slightly different than logistic regression. We're going to be now talking about Bayesian classification, which you may remember from the first lecture. We already said, okay, well, what is classification, and why not use the best possible classifier, right? The one that somehow omnisciently knows exactly what the probabilities are. Well, that's the Bayesian classifier indeed. It all relies on Bayes' formula, which we have here, where the idea is, or the magic trick is, that what we're interested in is the probability of our target given the input. But yeah, we don't really have that, right? But what Reverend Bayes back in a long time ago, I think it was 16 something, but maybe it's 18 something, I don't know. He figured out that you can break down joint probability distribution in its constituents, namely, what is now the probability of seeing an observation given a class? Well, that is something that basically comes down to counting, right? Conditional counting for the classification. What is the probability of y? That's the probability of a class to begin with. Okay, that's also something we can do. And the only thing that's a bit tricky, what is the probability of an observation? How do we know, right? What is the probability of this observation, of that observation? Well, we can do two things. We can either care really deeply about it, or we can say, like, shrug, every observation has the same probability, right? No. You can also, when you train your classifier, say, okay, there's something in the middle, because for my classifier, I have to go over every sample anyway. So for any classifier I'm going to train, the Bayesian kind, these PR of x's are all going to be the same, right? Regardless how I estimate them. So I just throw them on big heap, I ignore them. So let's unpack it again. The posterior is the one that we're interested in. We can take the probability of the input given the output. We have a prior probability on the output and the prior probability of the input. Now, like I just said, the prior probability of the input is essentially a normalizing constant. It's going to be the same for your data set. Well, we can kind of wish it away, right, if we're training a classifier on one data set. Now, of course, if we do wish it away, right, then we can replace it with any constant. Equality does not hold anymore, right? Only if we use the right value of PRX it holds. So if we just ignore it, then P or Y given X is what we say proportional to, and I don't have the symbol here on the slide, but I will add it in the ones that I upload after the lecture. It looks kind of like an infinity symbol that has been truncated. It's useful to know this symbol because you see it a lot in machine learning literature. So if you haven't seen it previously, it's good that you do. Often we just ignore the denominator, and then we have a prop 2. Okay, so what is this useful for? It's useful for insanely many things in data analysis, machine learning, and the likes. But if we're interested in classifying, okay, how can we operationalize it? Well, suppose that we have K classes, right? We could do binary classification, we can do many. The basics don't really change. So we're now interested in figuring out, does the class Y take label K for a given instance small x? Now what we need to compute is the following. This is the density of X for class K, so Y, that's the for. We have here a number of weird symbols. Which ones do we have? We have these F for K for a given X, as well as F for L given an X. These are the class densities. So what is essentially the probability of a certain class generating a data point? Right? What we're going to be doing, essentially, is for each class, we're going to think up a different distribution. We're going to allow every class to have a different distribution. And if these are indeed different, we're going to get, in general, different densities per point for different classes. That's what we have here. Okay, what are these pi's? These pi's are the prior class probabilities. What is the probability if you take a sample at random from your training data set to get class K? So we simply count. It's just simply count. 5K is just, well, this is how often it happens. We normalize, and there we are. Now these class densities, these F of K, we can of course say, okay, let there be a distribution. We still need to estimate it. How are we going to do that? What I'm going to be showing you in the next, let's say, half of the lecture, at least until the break, I suppose, I'm going to show you a class of methods called discriminant analysis. And we're just going to start with linear discriminant analysis. Afterwards, we're going to do quadratic. In discriminant analysis, what we essentially do, we follow the Bayes classifier and we plug in a Gaussian distribution. We assume that each class is, bless you, is Gaussian distributed. Is this likely to be true? Sometimes, right? Can we do better? Yes, of course. We can plug in all sorts of fancy distribution estimates, but we're not going to do this right now. We're not going to do this today, and actually in EML, or maybe near the end, you can interpret one of the methods as such. But the basic setup of a Bayesian classifier and instantiations of LDA, QDA, well, you can think a bit beyond what I've explained you today. Good. Now, once we have those things in place, we have pi of k, that's easy peasy. We have these f and these l of fk and fl of x's, these densities. Then classifying a point becomes easy. So we already saw, first lecture, what we should do, we should assign that class label for which we have the highest probability. So for which the probability of y is k equals k, well, is highest, right? That's the one we should do. Okay. Now, let's go to a more explicit example. Linear discriminant analysis. Why do I start with LDA? First of all, it's also one of those very basic methods that often works well in practice, even if its assumptions don't really hold for data. So it's a very good baseline. Second, it's again linear. It builds upon what we already know from regression, from linear regression. One big happy family. Okay. What we now assume is that every class is essentially a cloud in space, and these clouds, they're Gaussian distributed, right? So if we have a 2D picture, we have a nice Gaussian, there we have a nice Gaussian, and these are the two classes. And what LDA is going to do, it's going to find a line, a linear separator between these two Gaussians. And it's going to place that according to the Bayes optimal decision, so basically smack in the middle, where the densities of the Gaussians are going to be the same. I have an example in a later slide. Okay, so how do we now plug this in? Well, every class is Gaussian distributed. So all of a sudden, well, this f of k for x, well, we know what the density of a Gaussian is. This looks like this. So I have to admit, every time I see it, I'm again scared a little bit. But okay, I know this, I've got this, I've seen this before. Now, one of the key assumptions in LDA, beyond that we assume that things are Gaussian distributed, we assume that every class has the same covariance. So essentially, we have Gaussians floating around in space, and they have the same shape, right? They're either all, well, really Gaussian, like a circular blob, right? I mean, a ball, or if one of them is sort of more cigar shaped, then all of them are cigar shaped. That's our assumption. Not very realistic, of course, and we're going to relax that a little bit later in the lecture. Now, if we do assume this, then the Bayesian classifier, very simply, well, here we have the probability. So if we now plug this in, we have the prior probability, the f of x, that becomes this thing. So now we have this monster over here, and we have that one. Okay, well, of course you can compute this, right? And that, but it is not very nice to analyze. And if we want to understand a little bit how does this monster work, we have to break it down. Now, we have, of course, this nice exponent here. So if we take a logarithm, we can break things apart. So the numerator becomes this one over here. So the numerator is the top one, of course. This becomes this. And this is going to allow us to do some nice tricks. Because the denominator, it's not so important, as we'll see. It's the numerator that really matters, because we assume this standard, so there's the same covariance everywhere, right? So if I now have class 1 and I have class 2, then the probability mass that I get in the numerator, if there is a very big difference, I should go for the one with the higher probability. That's the intuition of LDA, right? Good. This is what I have here. Then the base optimal choice is to go for that one that has the largest discriminant. As a discriminant, this is this function that we just saw, and now I call it just delta of k. And now I look between the two classes, right? And I can do this between every pair. And if one of the classes really says, okay, this is mine, and the other says, okay, I don't really care about it, okay, then you clearly should go for the class that says it's mine, right? If you only, so let's say, I mean, both classes don't like the point equally much, right? It's basically both like, okay, I don't want it either, okay, then it's a toss-up, right? If one says, okay, yeah, I don't really like it, but it's okay, then that's going to be the class with the highest discriminant. So essentially, we look at every pair, and we look at the largest discriminant. That's what we're going to be doing. Now, this delta, well, I lied a little bit just a few seconds ago. I said it's the same thing we saw above. Well, it's the same thing above, ignoring all the fluff. That's going to be the same for all the classes. So I have a derivation for you if you wish, but if you, let's go just one slide back. If you look here, so x squared over the variance. Well, hey, this twice the variance, it's going to be the same, right? We just assume that away. UK over, yeah, variance is again going to be the same. So we can simplify this thing quite massively. And that's essentially what happens in the function that we have here. Okay, now let's go to the next example. Suppose that we have binary classification set up, simplest we can think of, and the classes are completely balanced. We have as many class yes as we have class no, right? Then how should we now classify? Well, obviously, or not obviously yet, but I mean, basically what we look at is twice x, okay, fine. The difference between, essentially the difference of the means of these classes, and then looking at variances. Let me show actually immediately here, because this is basically gives you the intuition in one go. We fit these Gaussians. I have here a green one and a red one for yes, respectively no. I have the means for these things, right? And then I'm going to see is essentially how close is my data point to these means. That's essentially what it comes down to. Of course, I also need to take into account the variance of these things, but they're the same for both, so that's not so very exciting. This is the base decision boundary, where we can't tell which one is which, right? So we should also always hope that we don't have too many points that are exactly in this point, but yeah, good. How do we fit these things? Because in practice, well, we can assume a Gaussian but what we have is just data, right? Now, relatively straightforward, because if I give you a bunch of data points, you have to estimate the mean. Well, we already discussed about that, right? Unbiased estimator of the mean, just take the average. So this is what we have here. The means for each of the classes, we can just, actually for all of the data, but also for each of the classes, we can just compute like that. We assume that the variances are shared over all data points. So why do we go here n minus k? Why do we not normalize by n? This is, again, we need at least one data point per class, otherwise we can't estimate anything, right? The same rationale as we had in linear regression, or which part positive was it again, for the statistical significance, right? We also divide it by, well, n minus p, because, well, n minus 1, because we have p plus 1 coefficients. If I ask you to learn a regression of a classification model over 10 classes, but I only give you examples for 2 classes, then yeah, what are you to do for the other 8, right? It's not going to work. So hence that is the n minus k. And then, well, we go over each of the classes, we go over each of the data points within this class. We see what is now the variation from the means of that class overall. There we have it. Good. What is then the overall? Well, this would actually be pi k. We'll fix this. So this is the prior probability of a certain class. This is the number of elements in that class divided by n. Now, if we have those, then we already have Gaussians, right? We're done. So LDA is very simple to fit. We don't have so many parameters. How many we have and how this now contrasts. So if we start to make it more powerful, we'll see in a minute. We assign x, a data point, to that class with the largest discriminant, which we now know how to compute. Now, this discriminant, I mean, it's not so much that I'm against calling in classification things discrimination, because that's what classification is about. We call something an apple or an orange, right? I mean, it really has to be this or that. That's what classification is about. I personally find discriminant a bit of a stupid terminology. I wasn't in the room when they decided upon it, but the most important thing to remember, it isn't just a line. It's somehow a separating plane in your input space. So if you have a 2D or a 1D example, it's just 1 point, right? If it's 2D, it's a line. If it's 3D, it's a plane, and so on and so forth, right? But it's just straight. That's the key thing in LDA. So it's essentially, it's the close cousin of linear regression in that sense, of plane regression. Okay, so far we've now looked at the simple case where we have only one predictor, and actually just also simple in the sense that we only have 2 classes. Can we ramp LDA up to the multivariate case? Quite straightforwardly. Essentially, the only thing we change is that we go from a Gaussian with just mean and variance to now we have a mean and we have a covariance that is a little bit more exciting than just a variance, right? So here I have 2 examples on the left-hand side, or right-hand side, sorry. Not when I'm looking at the screen, of course, but for you at the right-hand side. At the top, equivariant in both directions, right? Basically, it's a very undecided Gaussian. In the bottom, well, the predictors are correlated. Of course, if the predictors are correlated, we want LDA to be able to fit this, so we should allow this, of course. But personally, so when I was preparing this is a small aside. When I was preparing these slides, so in the previous iterations of the course, this was spread over multiple slides, and I never saw it. But now I put them on one slide below each other because I think it's easier to see now what is the difference, and otherwise you just have to flippity-flop back between slides. These boxes, these 3D boxes, they have the same shape. But when I look at it, my brain refuses to accept this. And the bottom one somehow seems flatter. Right? My brain refuses to accept that it's the same projection, but trust me, they are. I overlaid them many times just to check. Good. Okay, so now it's just not just the variance that's the same, it's the covariance that's the same. So the function, the only thing that changes is that here we now have a covariance matrix rather than just a variance. Here we have the covariance matrix again. There you have it. The discriminant doesn't become so much more exciting either. We just have covariance matrices, and there we are. Note that I jumped to matrix notation, because otherwise, I mean, the thing just blows up and then becomes very inconvenient to read. Sigma is the covariance matrix over all the predictors, right? We don't have to bother with the output. And well, we know how to estimate a covariance matrix from data. Good. This is essentially what LDA assumes. If you have, in this case, 3 classes, right? And well, they all 3 of them share the same covariance. That's what we assume, right? Whether this is now true or not, we just force it, right? So hence these well, what are they? I mean, a bit elongated circles. They have exactly the same shape, but they do have different means. Now, the dashed lines are again the Bayesian optimal decision boundaries, right? That's where we just simply can't tell is it the one or the other. So those are the discriminants that LDA is all about, right? In practice, let's suppose that this is now the true distribution, right? I mean, that's we don't know it, right? I mean, nature just gives us some data. Now we're so we need to estimate those things, and that means that we get some data points. For example, like this. This is on 20 samples. 20 samples is anything but big data, but in many cases, 20 samples is just what you got. Now you actually need to help me for a second, because I don't think I already spoke about the long tail, but maybe I did. Did I speak about big data versus small data and the long tail? No? Okay, good. Then either, I mean, you found the story that good that you wanted to hear it again, or I didn't. So let me see. So I personally, I really do not like hypes, and that's I like getting down to the basics and really understanding a problem, defining, grabbing it really by its tail, and that's answering real questions rather than just doing stuff. So hence I am somewhat critical of the whole deep learning hype. There's definitely something there, right? And in certain cases it's fantastic, but let's throw it at everything. No, that's not the right thing. A few years before, deep learning was all the hype. It was big data. Everything was about big data, right? And you had very stupid jokes in the sense that, okay, I mean, that big data is a little bit like sex for teenagers, right? Everybody's talking about it, nobody is doing it, right? And that, give or take, give or take. And actually that is true. There's incredibly few people or corporations or researchers who actually have big data. Big data is like, okay, well, more than fits on the computer, more than you can handle, right? There's very few instances. And that you have to think about the long tail. What is the long tail? Let's park big data for a second. Why did Amazon, as a book-selling company, become so successful? Why did it become like worldwide #1? I mean, there's a few still reasonable competitors, right? But why did they have really an edge over the bookshop around the corner? Yep. Marketing policy. Okay, yeah, maybe. Anybody else an idea? Accessibility. Yeah, you didn't have to go to the shop, right? So okay, well, advertising, accessibility. Anything else? Yes. Do what? Audiobooks. Audiobooks. Yes, that also. I mean, that's easier to download from an Amazon, from a website. Than, but no. Okay. Yep. You. Say that again. Sorry. The web store. The web store. Yeah. Okay. Range of products. Okay. Now we're getting a bit closer to what I was after. All of the suggestions were good, and they really help, right? If you have a shitty website, you don't have marketing, and so on and so forth. Yeah, what is going to happen, right? But range of products. Let's dive a little bit deeper into that. I mean, what do you mean by that, and why does this give them an edge? Exactly. If you're looking for some book, higher chance of finding it on a website, not necessarily Amazon, right? I mean, basically, this goes also for, let's say, if you want to buy some computer equipment, right? I mean, there's plenty of online stores that have way more products available than just your computer shop around the corner. This is a bit also why those disappear, right? Suppose that you are now running a real bookstore, right? Everybody loves books. You have only a limited amount of shelf space. basically to show books. Right? Which books are you going to put on display? The most selling books. Yes, I agree. I agree, right? And that is exactly the difference between a shop with a limited amount of shelf space, what they can show, and an online retailer. Because as an online retailer, you don't need the shelf space. You just get some giant ass center somewhere in the middle of nowhere, right, where you can basically have every book ever written right on the shelf. And if here we have the book that you want, right, it may have been there already for 10 years. And as long as we kept the conditions right in our center, right, I mean, then it's not like all moldy and stuff, so that we take care of course, costs a few euros, but whether we sell it now or tomorrow in a year, doesn't really matter, right? And with inflation, actually, well, we're gonna perhaps make more money. So, whereas if you run a brick and mortar shop, you'd rather go for the heavy hitters. You'd rather go for the Harry Potters, right? I mean, that's the 50 Shades of Grey type of books. Whereas, I don't know, I mean, that's fancy knotting or, I don't know, sewing or whatever your hobby may be, right? I mean, I'm not trying to, but that's a book that you might not find in the real store, but you will find it on Amazon. Now we're talking about the long tail. So if you now think about it, and if I now draw a distribution and also make sure that we see it online, essentially there is a big peak, right? So this number of sales, right? There's relatively few books that sell amazingly well, but that drops off really quickly. And then we have a very long tail of millions, billions of products that, well, don't get sold that often, but they do get sold, right? As long as you offer them, people will want them. And what is now an interesting effect is that if you look at the area, right, so basically the densities, under the heavy hitters versus the long tail, there is way more money to be made under the long tail than just the heavy hitters, right? Now, of course, if you have limited shelf space, that doesn't mean that you should all of a sudden put like really weird books, right? Because then nobody's going to buy them and you're going to go out of business. But that is the edge. That is the edge. The long tail does not just hold when you want to sell stuff, right? This also holds for tasks in general, and in my view, specifically in data analysis, machine learning, and the likes. So there are a few tasks where we have enormous amounts of data, right? Computer vision, in many, many cases we do. If you look at language, for English language, amazing how many resources there are. For other languages, way, way less. For some languages, we barely have anything. If you look at, for example, I mean, I've been working a lot with material scientists. So physicists who like materials, right? And they want to discover the laws of nature to build even better materials. They particularly often, they like solar panels, to make better solar panels. One of the tasks we were working on a few years ago was it again? Octet binaries. What does this mean? Essentially, you have two groups of atoms, and if you have to take one from the one group, one from the other, and then you put them together. That's the binary, right? It's two types. And then, well, you create lots of those molecules, and they're going to crystallize. And depending on how they crystallize, they are, well, you could say, more robust or more brittle. It's not really the case, right? I mean, harming reality a little bit, but you can imagine, right? But now, understanding why do sometimes, why do certain combinations crystallize like this and others like that? Because if you look at the atoms, like they kind of should behave the same, but they have very similar, very different behaviors among when you pair them up. There's 80 of such combinations. That's that. So effectively, you have 80 data points, and there is simply not more. And the dynamics of these things are, God knows, right? And that's not really a big data task. But it is a task. I mean, had you solved it somewhere in the 90s, it would have given you a Nobel Prize or something similar, right? But in the meantime, that particular task has been understood quite well. But there is an enormous amount of such examples where you have very little data, right? So in a way, in machine learning, it is not so much about the big data tasks, but it's more about the small data tasks. Now, one of the cool things, and this is where sort of my story then partially breaks down, but I'm going to be honest with you. One of the cool things that we've seen recently, thanks to deep learning, if you now train, for example, an NLP, natural language processing model, on English, And well, train, right? And we've seen GPT-3 and whatnot, and can hallucinate all sorts of text, but you can also translate things. You can then, with relatively little data from another language, you can often fine-tune it. So you don't have enough data to, for example, I mean, I'm from the Netherlands, right? There's much less data for Dutch than for English. I mean, plenty, but okay, let's stick with the example. So if we now learn a model for English, and then with a little bit of training data in addition, we can fine-tune it. And all of a sudden, we have a pretty damn good model for Dutch. That is pretty neat. That is pretty neat. Okay, so this works for language. This works for images. Data, where there is a lot of redundancy. So in an image, I mean, if I point at, let's say, I take a picture, I remove one of the pixels, and I ask you, what's going to be the color of the missing pixel? Probably most of you are going to be pretty good at it, right? Even if I remove almost all the pixels around where I sample, right? Because there's a lot of redundant information. Same thing in language. Language is hyper redundant because if it isn't, you would not be able to decode what I say unless you pay very close attention and I pronounce very clear and so on and so forth, right? Redundancy is king. In data where there is much less redundancy, these methods tend to fail. Coincidentally, these are also often the cases where, well, we don't have so much data. So my point being that there is a lot of fun to be had in the long tail, right? Small data matters, right? Don't just buy into the big data hype just like that. However, if you can leverage big data for your task, then there is a thing called the bitter lesson. So it's recently been postulated, I forgot the name, the researcher who proposed it. But basically the bitter lesson is that whereas machine learning researchers, also for these small data cases, or in general, they've been using a lot of brain energy to come up with smarter and smarter models that sort of exploit more and more things of the universe, of what we know, right, to get better performance. Now, the bitter lesson is that quite often, you can do this, but you can also just take a stupid method that scales, that becomes better if we give it more training data. And surely, or slowly but surely, this method is going to outperform your super smart method. And then you just give it more data and it's going to be even better. And you give it more data and it's going to be even better. So you need to pick your battles smartly, right? So hence, if you go for a big data task, rather go for a method that you know where you can prove will become better with more data. Don't put in too much of your own brain energy, right? Let the data be smart for you. But in the small data case, yeah, infusing some knowledge from the world makes a huge difference. Good. Just to, well, this was quite a long, not rant, but an aside, 20 samples per class may not sound so realistic. However, it very much is. And it's exactly for those types of cases, we would really like to have good, reliable classifiers. Now, obviously, in this case, it kind of works. You see the dashed lines, they're quite close to the dark lines. So let me see, actually, so the dark lines are close to the dashed lines. Those are the estimated ones. Will work quite well, will generalize quite well. All good, all fine and dandy, right? You see, it makes a few errors here. But yeah, even the Bayesian classifier would make those errors. All fine, all fine. Now, why can LDA do so well on so little data? Because this is ridiculously little data, because it makes such strong assumptions. We forced so much knowledge, between big quotes, into this model that it didn't need to learn so much from the data. The more we ask the method to learn from the data, the more data we need. Good. Okay. So now I'm going to take a sip. Yeah, so we have to estimate the mean. Mean is easy, and the covariance. I'm going to explain how that works. I hope you still remember that, otherwise you can look it up. Let's see. Okay, we'll get back. We'll get back to this in a little bit of time. Let's first go into an example. This one I perhaps should have animated a bit, but okay. So now we want to predict again if somebody is going to default, if they're not going to pay back their loan, right? And we take the credit balance and whether somebody is a student as inputs. And what we see is that the training error for LDA, whoops, where are you? 2.75%. that's pretty decent. That's pretty decent, right? I mean, that, here we have what we call the confusion table, where the prediction is no and the true is no. Well, look, we do very well here, right? And actually, if we say yes, well, 81 out of, so in 23 of the actual no cases we say yes, and in 252, oh, this actually looks pretty good, or does it? Or does it? Because the thing, of course, that we do notice, we look at this, that if we look at the total number of no's, it's almost 10,000, and the total number of yeses is 333 out of 10,000. So if we just have a super simple classifier, the no classifier, right, the trivial one, in this case the no one, that just always says no, we already have an error of 3.33. Okay, then 2.75 is obviously a little bit better, but So what we should do, we should now analyze how sensitive, respectively how specific our classifier is. What types of errors does it make? We need to be able to quantify this. Because just by looking at the table, yeah, there's definitely more cases where we say no, where it is a yes, than the other way around. But yeah, there is also there are simply way more no cases. So how badly, how good or bad is it? Before I continue, let me introduce a bit of terminology, because these 4 quadrants, they have standard names. When we say no, and it is no, that's a true negative. When we say yes, and it is a yes, it's a true positive, right? If we get it right and we get it wrong, but we get it right, then we have the true. And on the off diagonal, if we say no, but it is a yes, that's then a false negative, because we falsely said no. And then we also have a false positive. And then similarly, I mean, these are the total numbers of no's. So the negatives, these are the positives, and these are the predicted ones. This is relatively standard terminology. I mean, the N asterisk and P asterisk, perhaps you don't see it so often. Sometimes people use different notation there, but such is life. The other 4 you will definitely see in many books, many papers. We can use those to now determine the fraction of correctly predicted positives. So how good are we at finding positives? We take the true positives plus all the cases where we should have said positive, right? So the true positives plus the false negatives, where we said no, where we should have said yes, it comes down to this. That's the sensitivity. We can also look at the other way around, what is now the specificity. So the fraction of correctly predicted negatives. What is the fraction of saying no when we should say no? Definition is exactly the same. And now we can look at, and we can compare much more fairly these 2 classifiers, and we can determine, okay, is this something we want or not? So the no classifier quite obviously has no sensitivity, right? I mean, it's very insensitive, quite literally. 0%, 0 over 333. The specificity, well, it's very good at detecting the no's, right? 100%. Of course, we would like those to be somewhat in balance, right? The no classifier, you could say in modern parlance, is extremely unfair, right? Doesn't give anybody a loan. So you want this to be more fair. So you would like both of those to be 100%. And if you can't have that, well, then both high, but not as imbalanced as this. If we look now at LDA, let's look first at the specificity on the right, 99.8. That's pretty good, right? I mean, not quite 100%, but pretty good. This 0.2% that we lost here gave us, in a way, 24.3% gain in the sensitivity. So you could say this were a few errors well spent, right? I mean, it sucks to be those people that we now said the wrong thing on the one side, but there's so many more people in the fraction that we did the right thing for. Overall, what LDA tries to do, how it's defined, it's essentially the Bayes classifier, right, with some Gaussians plugged in. So it tries to minimize the error as much as it can over all observations, rather than, in this case, the no, right, which is, okay, I'm not going to make errors in the no class, and the rest will screw them. Now, we may or may not be happy with this balance, right? Maybe we say, well, let's say, so it's really a matter of life or death, right? I mean, that's, if I make an error in the sensitivity, so in detecting, let's say, somebody, let's say, most people, right, most people don't have cancer or like a life-threatening form of cancer. So the no classifier is already pretty good, right? You kind of would like to be able to detect those people who do have a nasty type of cancer, especially those cases that are treatable. So you don't want to have a very, well, specific but completely insensitive classifier, right? But you don't want to flip it the other way around either, right? If you tell everybody like, oh my God, you're going to die, right? And then, well, we do notice like, actually, it was not so bad, right? I mean, you're going to die, but it's going to take 80 years. Like, okay, come on, right? I mean, that's chill. You want to have a good balance between the two. So 24%, maybe we can crank this up, but that will be at the cost of spooking some other people. This is a choice that in the end, a practitioner in a medical case will then need to make. But in other cases, so what is the risk that you want to take if you're a bank? This is still the case where we want to give out loans. What is the risk that you want to take? You could even quantify what is the risk, right? When would I go bankrupt? What is the best case for me in order to make money, right? Okay. Now, before I continue, small aside, these false positives in the statistic literature, they typically call them a type 1 error. The false negatives are a type 2 error. And the joke in statistics is that the type 3 error is to mix up type 1 and type 2 because the names don't make sense. So I have a handy guide for you. Right? This, right? These two gentlemen, right? I mean, let's not assume genders, but okay, this is a false positive, right? And the other way around, type 2 error. It's a false negative, right? Okay, I know that the world has progressed, right? And that's that anything is possible, but perhaps this helps as a mental image to separate type 1 and type 2, but not pregnant versus pregnant. Okay, good. Well, so let's go back at the more serious case that we don't want to, well, spook too many people with you're going to die. And at the same time, we don't want to let all the treatable people just, well, walk into their grave because, yeah, our classifier was not specific enough or sensitive enough. So what we can do, we can trade sensitivity for specificity. We can trade these things off. And in LDA, this is relatively easy because it's essentially the balance between these two discriminants. Essentially, what we can do, well, let me put it this differently. Normally, the decision threshold between class no and yes is the base optimal one. It's at 0.5, right? So where we say that these probabilities are exactly the same, right? We can't say. I now think that I'm actually going to quickly go back to this slide, and I know now what I'm going to change. I was at 13. I'm going to go back to 6. Here we are. Essentially, if we say it is worse to miss a red one than to, well, so it's worse to miss a red one, so we need more red, right, than it is for a green one, then this boundary should be moved to the left, obviously, right? And the other way around. If we don't want to miss any of the green, then this one should be bound. This is not really a mathematical problem as such, right? To a decision to where to move it, but how we should move it, how far we should move it, that's a mathematical question that we can answer, that we're going to answer next. Good. So we can move the boundary away from 0.5. If we choose our boundary, so basically the probability at which we're going to say yes, below 0.5, well, obviously we're going to have more points there, and the other way around. Now, this threshold, there's essentially infinitely many possibilities, right? And what you now would, on the one hand, if you ask your expert, let's say the doctor, okay, what would be the balance? They might say, okay, get everything right. Yeah, but that doesn't work, right? That's the data or nature is against us. I mean, what can we do? Like, yeah, we'll choose the best one. Okay, but that's actually what my question to you was. What is the best one? So you're at the stalemate. You have to figure out what is the best balance, and particularly, the problem was, and what I said first, namely, it is not attainable. Which classifiers are attainable? Which balances between sensitivity and specificity are attainable? Well, in theory, what we can do, what you'll see that we will be doing in one of the next slides, we can hypothesize every possible threshold. Because a threshold at 1.0, would be a very trivial one. And then 0.9999, 0.99, and so on and so forth. And we all the way down in minute steps, right, all the way to 0. Then we have all possible classifiers that we can construct using, in this particular case, LDA, right, choosing the threshold. Example here, if we set the threshold at 0.2, we get a sensitivity of 60%, and the specificity is still 97.6%. So yeah, we threw a few people under the bus, or the other way around, but we now get more than half of the people who actually do have the horrible cancer, right? We can now treat them. That's nice, or nice, I mean, hopefully. The overall error of this classifier is now worse than the trivial one. Just to illustrate that sometimes having a worse error can actually be beneficial. Realizing this, right, the moment you realize this, and this is why, again, why I'm so happy with this book, this is what fairness is about, right? Fairness is not about just blindly maximizing accuracy. It's about thinking about policy. How are things going to be implemented? How are things going to be used, right? Having a classifier with a better accuracy does not necessarily mean it's better in practice. Good. Yeah, so these are just the examples of 0.5 and 0.2. That's so interesting. Okay, so now getting back to what I was saying, so here we chose 0.2, but we can of course do this for every possible threshold, right? And we don't really want to do this by hand or anything, but what we can do is actually plot for each of the thresholds from 0 to 0.5, and note that if I go beyond 0.5, then basically the thing flips around, right? It's not so exciting. I can plot the error rate. And of course, I mean, it becomes extremely bad at one moment. I can also plot the false negative rate, so then it's not error rate anymore, but okay. So how many points do I falsely say are a no, right? Even though they're a yes. And I can look at what is the false positive rate. This could be something we could do, right? And somehow on this plot, we can try to figure out, okay, where is the balance, right? I mean, what sensitivity do we want? I want the sensitivity of this, but yeah. This is not very intuitive, this plot, right? It gives you all the data, but not really in the right way. For that, we have receiver operand operating characteristic curves, or ROC curves. And what we now do is, rather than plotting the error for different, no, we plot very simply the false positive rate, so 1 minus specificity, in the y-axis, or the x-axis, sorry, and the sensitivity as the y-axis. And what we now get is that for every possible threshold, right, this is now a dot in this space, because for every possible threshold, we can compute what is the sensitivity or the specificity. That's the dot, right? So if we now connect those dots, it would look like a mess, because I'm going to have dots all over the place. All sorts of bad combinations, bad thresholds, right? But all the ones that I'm now blipping here, right, or here, I'm not interested in. I'm interested in the best combinations. And that is the nice thing. This plot also shows the best possible classifier, the one that we would really, really want, which has both a sensitivity of 1 and a specificity of 1, right? Top left corner. So that means that if we now, starting from the bottom left corner, right, we don't make any decision, so it's never going to be good. If we now take the Pareto optimal front, we basically find the, what is it? The convex hull. The convex hull. We basically draw the line. So basically, we only take those classifiers, right, that do so well that we can't improve over them by choosing another one, right? I mean, for that particular value of 1 minus specificity, respectively this. So that line, that's the blue line that we have here. Those are all the, and we just connect those dots. We connect those dots. That is the, well, the curve, right? That's the ROC curve. And for a given classifier, what you can now do, you can compare not just on error, not just on accuracy, which depends so much on your thresholds or whatever parameters, right? And that, but you can really compare, you can really look at this classifier now, how good is it in general? And the other nice thing is, we don't do it here in the slides, but if I now have a competing classifier, I get another curve. And there's two things to be said then. First of all, we can, well, suppose that I now have another curve that looks like this. So it's really below always, right? Maybe in the top it will meet it, but it's below the blue one. So let's say the blue one is LDA, and the one that I just indicated would be my discriminant JDA, right? I mean, nobody would want to use JDA. It's stupid to use it, right? LDA. Now, in practice, what you're going to see is that, for example, JDA will be worse here, but will be a bit better there. Now, what is now a nice trick? Based on sensitivity specificity, this really goes beyond what we do in EML. You can somehow merge these two classifiers in a probabilistic type of sense that we can really get the best of both worlds. Anyway, that I'm going to skip. Right now, we just have one classifier. And the only thing I wanted to say is that you can evaluate how good a classifier is by looking at this curve and calculating the area under it. It's the area under the curve, AUC. And that is, in general, a much better measure of performance of a classifier than just accuracy or just error, right? Because rather than looking at the one threshold that you chose just by chance, you look at every possible threshold. Good. Yeah, exactly. One other thing that's also important. So if you have just a random coin flip, right, the most stupid one, we also know what the AUC is. That's namely just going to be under the diagonal, right? You just always do random things. So there you have it. Up. Yeah, if your curve goes below the diagonal, then you can just take the opposite of the output, and that's good. This is the point where we actually wanted to go, because why did we need to tinker with this threshold? Why did we even consider doing that? Because, hey, Bayesian optimal classifier, right? Why? The data was incredibly unbalanced. And then just by plain mathematical probabilities, you might become unfair in practice. That's what we actually wanted to do, right? We wanted to have a tool to weigh this. And ROC curves are not influenced by imbalance of the data. Just locations of thresholds move a little bit, but in general, it's the same. Good. That was it so far for LDA and thresholds on LDA. Let's take a short break, say 10 minutes or so, right? And then we continue with, well, QDA. And then we're going to evaluate a little bit how good all these things are, and then we're done. Yes? Let's see you in 10 minutes. So 22 past. Good. So now I'm going to continue with the lecture, ROC curves. Bam. So linear discriminant analysis, well, linear schminier. Why don't we actually give up on the assumption that the covariances of all the classes are the same, right? I mean, let's be a little bit more inclusive there. For LDA, the density function looked like this, right? And the discriminant like just below. So density and then, well, definition of the discriminant. If we now replace the having one covariance matrix over all classes, that's the same. If we now let that go, then we have what we call QDA, or quadratic discriminant analysis. What are the main differences? Well, let me help you there. Now I gray out those parts that actually are just completely the same for both. And the only real difference that we have is here we have a slightly different term than we do have here. And well, this one corresponds essentially to this one, but right now it's class-based and we need to correct it slightly differently. Not so much changes, not so much changes, right? It's just that the right-hand side, in a way, we could simplify a bit further. Good. Now, what does this mean? Besides that the formula becomes a little bit more daunting, the class boundaries now all of a sudden become quadratic. They become curves, which of course can be quite beneficial. We of course do have to now fit a different covariance matrix, or we need to estimate it per class. So with 20 data points per class, yeah, maybe not, right? So essentially what we will need to do, we need to estimate many more parameters in QDA just by giving up this assumption than we had to do for LDA. How many more? This can actually be computed quite easily. Here I have it. So here we need to do it for every class. We need to estimate the covariance plus the the parameters of the Gaussian, or the mean, and this is then if we sum everything up. Okay, how bad is this? If we have 4 predictors, and we have 2 classes, LDA has 18 parameters, QDA 28. Well, that's not too bad, right? If I now double the number of predictors, but I stick with 2 classes, LDA has 52 parameters, already starts to become more serious, right? For 20 data points, bye-bye. QDA goes to 88. So there's a nonlinear increase there. If we, I don't have it on the slides, but I have it ready here. If we stick with 4 predictors, but then now increase the number of classes, go to 4, then 26 versus 56. If we now have 8 predictors, which is not even that much, right? Not that many, and we have 4 classes, LDA has 68 parameters, QDA 176. So all of a sudden, well, it's not that we exited the long tail, right? But we have to creep more to, well, the bigger, the heavier hitters, right? Just to show that a stupid assumption like LDA makes, covariance is always the same, it has, in this case, positive implications, what we call the sample complexity of the method. How many data points do we need to effectively estimate everything? QDA has a much higher sample complexity. Let's look at an example. So it'll take a few seconds to load. Here we are. So on the left-hand side, so for the same data set, right? On the left-hand side, we have the Bayes optimal decision boundary. And on the right-hand side, these are different data sets. Right? Yes, these are different data sets. I'm also a bit confused because, anyway. Left-hand side, the 2 classes have the same covariance. Right-hand side, they do not. And as you see, the Bayes optimal decision boundary now really becomes curved. So QDA sounds like a good idea on the right-hand side. Let's first fit LDA. Left-hand side, well, does a pretty decent job. Right-hand side, well, it's not horrible, but it's not great either. If we do fit QDA on this, so we estimate the covariance metrics for each, and then we just run the same machinery as we've seen. On the left-hand side, we see that it overfits slightly. It's not really horrible, but right? Whereas on the right-hand side, it does a pretty good job. I mean, it approximates the Bayesian optimal one quite decently. So left, QDA overtrains. Right, LDA undertrains. That's essentially what you see here. So if your problem is really linear, yeah, you don't need, and actually you don't want to have to estimate these additional parameters. And the other way around, yeah, if the problem is not linear, then yeah, good luck, right? Bias and variance, errors and variance. How do we fit these things? ESL, so green cross, ESL is the better reference for this particular part. Again, we simply estimate this from the data. So the means, it's not so exciting. Covariance matrix overall, this is how you sample it, which means that if we now look for one specific class, we just compute this now over just over those instances of that particular class. We still subtract the K. Actually, I'm right now not 100% certain. I would have to check the book. And if I made now an error in K here, I'm going to update the slides. If this should not be -1, because for this one class is only 1, and then for every class, no, it should still be K. It should still be K. Anyway, I'm going to double check it, right? But I think it should be K. The prior probability for class, well, that didn't change. No. Whereas previously, we could just work it out quite nicely. In the multivariate case, just like in linear regression, multiple linear regression, you don't want to do this to yourself. You rather go for matrix notation. So, and the covariance matrix that we have over here, or the estimated one, we can actually get relatively easily through a decomposition, eigenvalue decomposition of the data, where UK is P by P matrix, dk is a diagonal matrix, where we have on the diagonal the eigenvalues. So you do an eigenvalue decomposition, build this matrix, and there you are. And then UT, that's just the data again transposed. Now, if we decompose this thing as follows, we can use this in the definition of the discriminants. This is basically what we had previously. We're now going to just plug in a few things. So this term, this now turns if we look at this, into simply the sum, the logarithms, over this diagonal. Because the left-hand side, right-hand side, they cancel each other. We're working on the diagonal, these eigenvalues, right? Those are the things that we're interested in. And, well, we're also not interested in the order of them, right? That the matrix D has an order, this is great for it, but we don't care. We just sum the logs of these eigenvalues. And that's this term. Then this term over here, this monster, we can also rewrite in terms of UT. Again, the discriminant matrix and UT. Here we have the differences before the means, because the means, those are going to be simple to estimate. This is the definition of the discriminant, and the final thing, the log of the prior. I mean, okay, that I believe that you can get done, right? So we can now relatively straightforwardly compute this, plug it in, run it. And of course, I mean, in all your cases, if we just want to run it, it's all implemented already. If you want to understand it, then we have to study this a little bit. What is now the LDA estimator in light of this? Essentially, we normalize the data first into some, well, to share the same covariance. So basically, we force it to be one big sphere. That's essentially what we're doing. And then, in general, we always classify a point to the nearest centroid, the nearest Gaussian, because that's going to be the one that gives us the highest density. Good. That's it actually for LDA and QDA and how we can fit it. There's not that much to it. This is stuff that work a bit through the math, implement it, right, just to see how it works, play a bit with it. That's that. But should we actually bother with LDA and QDA? I remember having, well, I'm not going to say quite fierce, but we had some discussions. Isabel Valera, the machine learning professor, with whom I used to co-teach this, but right now she's on maternity leave. And she was a big fan of ditching LDA and QDA. And I said, no, we're going to keep it. And then, well, let's say, well, right now she's on maternity leave, so I could do whatever I wanted. I could convince her before that, because that would be a bit bad, right? I could convince her that actually this showing that by just having a few more parameters, things already go haywire, right? By making a ridiculous assumption that sometimes this is actually the better thing than having many more parameters. That is essentially why it's still in. Plus, I think it's a great illustration of how to instantiate the Bayesian classifier. Bayesian classifier itself, we cannot attain, right? We don't know all these probabilities. We don't know the distributions, right? We need to make assumptions. LDA, QDA are, well, your first meetup with an instantiation of those. Good. Now let's see how well they fare. In other words, I mean, these are going to be the arguments that Isabel used to ditch it, except for specific cases. We're going to be comparing different classifiers. So we've seen over the course of the last, well, this week, last week, and dipping into the very first, we already had the k-nearest neighbor classification. So we've seen k-nearest neighbor, we've seen LDA, we've seen QDA, and we've seen logistic regression. And we're not going to talk about linear regression, right? Because we already saw you get negative probabilities, it's weird. We don't need it. When should we use which one? Okay, well, LDA, of course, makes a lot of sense if we know, or we have some evidence that the classes have a shared covariance, right? And there is they're linearly separable, right? Then LDA is a good idea. But that's also a pretty good case for logistic regression, right? Logistic regression loves linear because it's essentially linear regression under the hood. Now, there's, of course, a bit of a difference between logistic regression and LDA, but at the same time, they're almost joined at the hip. So if you just look at the simple binary setting, then of course the probability for class 2 is 1 minus the probability for class 1. If we focus on that and we look at the log odds, it's the difference in this particular case of the two discriminants for LDA, so here, log of the odds, we essentially difference of the discriminants, okay? Whereas for logistic regression, if we do that, we have the two betas. Now, this also shows that both are fitting a line, right? I mean, logistic regression, it's also a line that it fits, right? In this simple bivariate case. And LDA It's also just a line in this particular case. But the coefficients are chosen slightly differently. That's why I chose purposely C and beta, right? I mean, you could, of course, also call the C's beta, but we choose them differently. How do we choose them? Well, the betas, logistic regression, we maximize likelihood. Right? Remember the convex or the concave problem, where we hoppity, 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 climb the hill, or we go into the valley. Whereas in LDA, the parameters, or what is now the line, right, is essentially chosen by where do we put our Gaussians and which shape do we give them, right? So essentially, they're defined by the mean and the variance of these Gaussians. This is how we can, if I move around now the means and the variance, this is how I define my line. That's what these C's are. So similar yet a bit different. Now, in practice, they often, but not always, give the same results. Before I continue, actually, I can say, okay, LDA makes stronger assumptions. I mean, yes, obviously, right? I mean, the world is Gaussian. Why do you think they don't necessarily give the same results? Versus, can you give me some intuition why you think, or maybe you have the answer already at the ready, why logistic regression is in general the more powerful and the more useful of the two? What? You're not sure? Okay, that's not the right answer. Yes. I see. Okay, well, it's not the right answer, but it is a very good answer to illustrate that it's not so much that LDA doesn't cover all of the data. What we drew was just an outline of the circle, because in the end, I mean, a Gaussian has probability mass everywhere. So it can predict any point. It learns from every data point. That's one of the other tricks that the Bayesian classifier does. It learns maximally from all the data. So in that sense, perhaps the picture that I showed was a bit confusing there, right? So, does anybody else have an idea on why can we, well, let's say, level up? Let me use that word then. Why? How can we make logistic regression perform better than in many cases LDA can? Let's recap. Logistic regression is essentially linear regression with a fancy activation function, right? And that's okay. Linear regression. Is linear regression strictly linear? Yes, but no, right? We saw that if you use the right basis functions, for example, a polynomial, then all of a sudden we can level it up, right? We can have quadratic, cubic, whatnot. Can we have interaction? Yes, we can, right? These are all things that, well, for LDA, not really that easily, that naturally. You can provide it, but it doesn't come so naturally. You can quite easily give logistic regression quite a few of those basis functions, and we'll figure it out. We have the statistical machinery to tell, okay, use this one, don't use that one, right? So logistic regression is a bit more versatile in that sense. Okay, let's park that thought and we'll see how it works in action, if we don't do all these fancy things. What about KNN? Well, KNN has the benefit, compared to especially LDA and QDA, it's non-parametric. It doesn't make assumptions like it's Gaussian, right? Which, of course, if the world is Gaussian, is going to work great, but if it's not, okay. KNN is one of those methods that scales very well with more data, right? But the more data, I mean, just you have the bigger chance of getting the right neighbors, and then you have the right prediction. So it's one of those horrible methods, right? It's very bitter in that sense. However, KNN is less useful for us if we want to learn from the data. Because with both logistic regression and LDA, when we get a model, we can look at the model. We can see, okay, what is now the discriminant, right? What are the parameters? get some insight. It may be wrong, so we need to test how right is it, but we get some insight. With KNN, like, yeah, these are the neighbors. Like, yeah, thank you. This is something I could have looked up in the data myself. Now, QDA, why do we write here? It's a compromise between LDA and KNN. It's more LDA ++. It's a slightly more loose LDA. It still assumes things are Gaussian, but because there's a covariance matrix allowed per class, and if a class is not very Gaussian, okay, then it just uses a very weird covariance matrix. It's all fine. It doesn't affect the others. So in that sense, it's a bit more relaxed than LDA. That's the compromise. Good. In the next few minutes, I have 5, 6 more slides, 6 if I count correctly. I'm going to go over 6 scenarios relatively quickly, and then we see when in those does what method shine and why. So in all setups, I have around 100 random trading data sets, all of which have 2 predictors and all of which have 2 classes. Simple, right? 20 observations per class in a data set, 40 data points. And why do I now repeat this so many times? Because for each of these random cases, I can now, for example, here for KNN, where it's basically 1 NN, I can look what is now the test error, and I can look at what is the distribution of it. For one data set, I would get 1 point. Right now, I get a nice box plot that shows me, okay, on average, this is roughly the error in the setup that you're going to make. We're going to be changing the scenario of how we generate the data a little bit. We start with different classes, uncorrelated normal variables, so it's Gaussian distributed. Different means same variance. Okay, basically LDA. So what do we expect would go best? LDA. What do we see? Yes, LDA does best. But, KNN, in this particular case, not so great. Well, this is just the one nearest neighbor. You would expect it to have a very high, which is it, was it again? Variance, exactly, yes. But so it's not going to do very well here. But if we choose through a method called cross-validation that you will see next week, slides are almost done. I will record the lecture tomorrow, and I might then immediately put it online. Perhaps I need a bit of editing, let's see. If we tune the value of K in a smart way, we can drag the error down, but we can't really beat LDA because this is made for LDA. Logistic regression, as you can see, slightly different, but it gets the same gist. QDA overfits a little bit. Okay. Next scenario. Now we have a correlation between the predictors. So it's not a blob anymore, it's now a cigar. Otherwise, it's still LDA because both classes have the same cigar shape. So we have essentially the same. We could have skipped this entire scenario. Scenario 3. Right now, I changed the way how I generate my predictors. It's not Gaussian anymore. They're going to now be t-distributed. And remember, t-distribution is a slightly less tall, slightly more, I'm not going to say fat, but I mean, chubby is also a bit, it has heavier tails. That's the technical term. So essentially, it generates more extreme points, extreme values, than a Gaussian would. Right? So basically, LDA should be less happy. And we see that's exactly the case. Right? Logistic regression does not make a parametric assumption that has to be Gaussian. All of a sudden starts to do a bit better. QDA also really doesn't like it because it's not Gaussian and the covariance. Okay, good. Full scenario. Right now, I'm going to have different covariances per class. In the one class, I have a positive correlation to the predictors. In the other, I have a negative. So basically, I have cigar shapes that are in a different angle. LDA hates that, right? But, they all hate it except for QDA because this is exactly what the QDA setup is defined as, right? So it outperforms all. But you also notice right now, right, that actually, so this is actually a good slide. So to illustrate, I copied this from the book. I don't come up with all the examples myself because to keep things a bit self-contained, and that you can also look it up in the book. But in the tutorials, we gave a bit of background on visualization. right? And I mean, which things can you use and whatnot. And one golden rule in data visualization, if I show you a bar plot or a box plot in this particular case, make sure, if any which way possible, that the origin starts at 0. Right now, what we're doing, if I now go between the different slides, right, each of those have a very different scale. So we could identify which one is best, but we are unable to tell, well, which one is now betterest, if you know what I mean, right? There might be a case where it loses massively, and yeah, maybe it's a very small loss. Here, scale 0.25 to 0.45, 0.15 to 0.30. So all of a sudden here, right, LDA is really much better, right? But, so keep this in mind, not just for this example, it's all fine, but whenever you read any literature and you want to decide, is this a good method or not, right? Be it during your studies, be it after your studies. Many people plot stuff like this, right? Even though this should be a capital crime. And whenever you plot something, make sure that you use as zero-centered origins as possible. Right? One of the tricky things is, of course, in these particular cases, had I done so, and this is why in a book where it doesn't really matter so much about the exact values, all of a sudden everything would have been way up. And then it means that I would have had to rescale things and everything becomes way more squished. You can't really see the details. That is often, depending on what your message that you want to convey is, the better choice than, well, losing comparability or between figures, right? Good. So 0. 0 is important. And if not 0, in the caption, say what you're doing and why you're doing it, right? Because you don't want to trick people. This is also one of the key things that in many, so if research papers are submitted and you want to show that your method is better, then we have, let's say, 0.99 and 0.9999, right? And oh, look, there's so much difference. Whereas, yeah, there's no statistical significance. Good. Okay, scenario 5, we're going to add a bit of interaction. Right? No, wait a second. This is QDA, this is also QDA. Okay, this is still mean the quadratic bound. However, what we see now is that k nearest neighbor in a very, well, because of the interactions that we have, the quadratic forms here, it is really not linear anymore. So these guys start to suffer. Okay, and then in a way, it's not so much better. It's just, well, pretty much as bad as it was. It's more that the others became way worse. And that is what you always see with KNN. It's not necessarily the best of the best, but it's not going to be super bad. And in order to beat not super bad, you need to often highly engineer something, and that's going to come at a huge cost. And of course, I mean, well, quite often the dependency of your data are going to be quadratic, cubic, or whatnot, right? And then in order to be not bad, it becomes the harder and harder to beat it. Final scenario, and then we're done for today. Here I take a complicated linear function, lots of combinations of things. So it's still, logistic regression should be kind of okay. And you see that, oh, it's quite okay. This one's quite okay, but k nearest neighbor, in the end, doesn't care so much, right? So basically the others, the complication, they suffer from it, and k nearest neighbors just doesn't suffer so much. Right? It can take really a beating. So in a way, that is how we can characterize k nearest neighbor. It's not the best unless you have infinite data, then why not use it? But otherwise, it's very difficult to get it off balance. So, and if we now just go back, so in the cases where it did lose, for example, here, why did it lose? Yeah, because we're now really in a case where the others have an advantage, right? We really tailored it exactly to those. But the moment we go to cases where this tailoring doesn't work anymore, so now ignoring the green one, it becomes roughly equally good, and then it becomes better and better and better. K nearest neighbor is a very good baseline. And on that, I want to end today's lecture. So unless there's any further questions, which I'll be happy to take after saying, see you next week. Well, actually not going to see you next week, but I'm going to see you in 2 weeks. That's also going to be my final lecture for EML. Yeah, but I might drop by now and then just to see, I mean, if Alexander is treating you well and whether you are treating Alexander well. Very important. Good. Thank you very much for your attention. Cheers.